Muy buenas tardes a todos ustedes, ingenieros que nos acompañan el día de hoy en esta gran maratón de puentes. Antes de continuar, me gustaría pedirles un favor y es si están escuchando bien mi voz, por favor pueden reaccionar levantando la mano. Bueno, veo que ya algunos están reaccionando, muchísimas gracias por confirmarlo. Quiero dar una breve introducción sobre nuestra compañía antes de iniciar con el webinar, sobre todo para poner en contexto a aquellos que nos están acompañando por primera vez y para que ustedes tengan conocimiento de lo que estamos haciendo actualmente alrededor del mundo y sobre todo para Latinoamérica. Bueno, ingenieros, les comento que Midas es una compañía que nace en Corea del Sur en el año 1989. Nos establecemos en Latinoamérica en el año 2018 en la ciudad de Medellín, Colombia, que es la oficina desde la cual nos estamos comunicando el día de hoy. Contamos con una red global de 10 oficinas regionales y distribuimos nuestros productos en 120 países. Actualmente tenemos más de 22.000 usuarios alrededor del mundo y en Latinoamérica contamos con 500 usuarios. Somos líderes en el mercado asiático, somos número 1 en los Estados Unidos en el área de puentes y queremos hacer lo mismo en Latinoamérica. Estos son los programas que estamos distribuyendo actualmente en nuestra región. Nuestro programa estrella en los Estados Unidos y en Asia, Midas Civil. Nuestro programa para estructuras Midas Gen y nuestro programa para proyectos geotécnicos avanzados Midas GTS NX. Quiero también darles una información adicional. Este año vamos a estar realizando la segunda edición del Simposio Latinoamericano de Puentes. Se va a realizar en la ciudad de Bogotá, capital de Colombia. Vamos a contar con invitados internacionales y la invitación es a que ustedes, aquellos que les encanta promover esas nuevas tendencias y dar a conocer sus conocimientos, puedan convocarse. Estas son las líneas temáticas que vamos a tratar durante el evento. El evento se va a realizar los días 15 y 16 de agosto y si ustedes escanean este código QR van a ser redirigidos a un formulario donde van a tener la información más ampliada y donde pueden inscribir tanto sus ponencias y les cuento que en caso tal de ser seleccionados nosotros cubriríamos todos los gastos de desplazamiento hasta la ciudad de Bogotá, alojamiento, alimentación y unos beneficios adicionales que vamos a comentarles una vez ya sean seleccionados como ponentes. La convocatoria va a estar abierta hasta el día 30 de abril. Hasta ese día vamos a recibir todas las postulaciones. Luego vamos a pasar a un comité en el que van a seleccionar las ponencias. Tiene que ser una ponencia relacionada con alguna de estas líneas temáticas y si ustedes necesitan más información sobre este evento, por acá también voy a compartirles mi contacto, mi teléfono y mi WhatsApp. Estas son también nuestras redes sociales para que nos puedan seguir y puedan estar al tanto de todos los eventos que vamos a estar realizando durante el resto del año. Bueno, ingenieros, entonces dando continuación a esta gran maratón de webinar de puentes, el día de hoy vamos a continuar con nuestro segundo webinar acerca de lecciones aprendidas con fallas de puentes en los Estados Unidos. Este webinar va a ser realizado por nuestro querido ingeniero David Liu. David cuenta con más de 25 años de experiencia en diseño estructural y análisis de vigas de acero, vigas de cajón de acero, cerchas de acero, vigas de hormigón pretensado y puentes posttensados. Espero que disfruten esta segunda presentación y damos inicio entonces. Muchísimas gracias.
Thank you very much for the nice introduction. And also I'd like to thank Midas to provide me this opportunity to give a presentation. The Then the topic of my presentation today is lesson learned from bridge failures in US. The purpose of this presentation is to provide some lesson learned for bridge engineers so we can learn from it and to make sure they won't happen again. Here's an outline of my presentation. I will start with the Tacoma Narrow Suspension Bridge, which is the most bridge failure in the world. It's a suspension bridge. The failure is due to the vibration. And the second one is the recent steel bridge collapse on I-90 near Philadelphia about 3 months ago due to a fire caused by a truck. The third one is Florida International University Truss Bridge collapse during the construction. The fourth one is the Sunshine Skyway Truss Bridge collapse, which leads to us to adopt the vessel collision design specifications. And the next one is the Cypress Street Viaduct. It's a pre-stressed precast concrete beam bridge collapse during this earthquake in San Francisco. Then the next one is the Civil Bridge. It's a truss bridge collapse due to the I-bar. It's a fracture critical member collapse, which leads the U.S. bridge inspection program, like to perform the routine bridge inspection every 2 years, once every 2 years. This next one is the Slabtown Road Steel Bridge over US 30 in Ohio. This bridge is caused by the collision when a truck is too high, while it exceeds the minimum vertical clearance, so they hit the steel girders. Then I will talk about a bridge collapse. It's adjacent box beam bridge collapse due to the corroded steel strand. Then I will talk about collapse of I-35W bridge, which is a very famous bridge, like a deck truss bridge collapse in 2007, caused 13 people dead. Then I will talk about Marcy pedestrian steel bridge collapse, which is due to the steel girder buckling during the construction. And then the next one, also the girder collapse in San Cruz Bridge in Arizona during the precast pre-stressed concrete beam bridge construction. Then I will talk about pretty famous Vocoda Sacramento Bridge. The contractor found some cracking in the web of the Sacramento box during the construction. Next one is the Leo Frigo Memorial Bridge. This one is, there's like a big settlement at the pier due to the corroded steel piles. Then the next one is, the next one is the Schoharie Creek Bridge collapse due to the scour issue. My screen freezed. I cannot. Hold on a second. Okay, the last one I'm going to talk about is it's a bridge on I-75 bridge collapse during the demolition of the bridge. So I pretty much cover everything from design to construction, everything. So what are the causes of the bridge failure? Well, due to collision, like the one in Philadelphia, that's the one. Well, that's not the, sorry, the Slabtown Bridge, that's one due to collision. Then floods, the second last one, that's the floods will cause scour to cause the substructural failure, may cause the bridge collapse. Unexpected events, accidents, construction incidents like the last bridge failure. Then design flaws and the manufacturing errors, fires, that's the one happened 3 months ago in Philadelphia. Of course, the last one is due to the earthquake. Now I'm going to talk about the most of bridge failure. Tacoma Narrows Bridge. It's a suspension bridge built in, I think, around the 1938 or 39. About the same time when they built the lines, the Golden Gate Bridge in San Francisco. I think that this bridge failure is due to the vibration, because the superstructure is too shallow, and the resin, I forgot how many people died during the bridge collapse. This bridge failure leads to wind tunnel testing for all the major bridges, like a suspension bridge, cable stay bridge, long span arch bridge. So from the wind tunnel testing, then you can get all the aerodynamics characters to make sure the stiffening girder is deep enough, and also the shape of the superstructure is good enough, so to prevent the resin or the severe vibration of the bridge. This picture shows the steel bridge collapsed on I-95 near Philadelphia about 3 months ago due to a fire from a truck. So you can see, because the steel girder, they cannot resist the fire well. Pretty much like a World Trade Center. When 2 planes hit the World Trade Center, the 2 buildings collapse. When you have the high temperature, the steel girder will lose its capacity. This picture shows the repair on this bridge is unusual. They pretty much just close down the bridge, the roads under the bridge, then they put the field with some like a fiberglass or some special field, so they can, that's the quickest way to open the bridge, because otherwise if you try to replace the superstructure, it may take much longer to have the bridge open. This picture shows the bridge collapse at Florida International University. I think it's a truss bridge. They are using ABC, so combine a little bit everything. So before the bridge collapse, they notified the bridge designer, there be cracking, but they didn't close the bridge right away. So that's the problem. This is the Sunshine Skyway Bridge. I think the existing bridge is a truss bridge. I think because this boat hit the pier, so caused the bridge collapse. So after this, then AASHTO include the vessel collision design specifications. So make sure when you design the pier, or you have to design some dolphins or something to, or design the pier to take some the vessel collision loads, to make sure they can take the loads from the boat. This is a Cypress Straits Viaduct collapse. It's a pre-stressed, precast concrete beam bridge during the earthquake collapse. I think mainly you can see the column, maybe they don't have enough confinement. So after that, it leads lots of seismic design improvement to make sure that the column is ductile enough to take the seismic load. This is a very famous civil bridge. It's a truss bridge. The bridge collapsed due to the eyeball intention. It's a fracture. Well, we all know the truss bridge, all the tension members are fracture critical members. So as long as one member collapses, the whole bridge will collapse. So from this bridge failure leads US to conduct the bridge inspection once every 2 years. This is the Slaptown Road Bridge over US 30. You can see the steel girder is bended due to the was hit by a truck, overheight truck. So I think in the future, I'm suggesting right now everywhere you can see the way station for the trucks. I think they might have to check the truck vertical clearance, make sure they won't hit the bridge. So this, I didn't see any posting for the vertical clearance, so I assume should meet the minimum vertical clearance required by the DOT, but still hit by the truck, which means the truck is way too high, way too tall. Yeah, this is a bridge failure from Pennsylvania. It's an adjacent steel box girder bridge. I think that for any bridge built like 30 or 40 years ago, there's an issue for the steel strand for the adjacent box girder. I don't know. Either maybe the concrete cover is not deep enough or some other reason. So there are quite a few bridge failure due to the corrosion steel strand caused the adjacent box girder bridge collapse. So this picture shows the steel box girder section. The red is the corroded strand. You can see most of the strands at the, I believe this is at the center span, so you can tell the box beam lose lots of capacity while severe corroded. But it's tough to inspect. I think Illinois DOT, I think they improve their adjacent box girder details to make sure, to mitigate the steel strand corrosion in the future. This is a very famous collapse of I-35W bridge in Minneapolis. It's a deck truss bridge. I think their finding is one gusset plate is under design. The bridge was designed in 1960s, and the cause of 13 people dead. I heard that the victim sued the DOT for $10 million. Then the DOT sued the company for $10 million as well. Here's another picture shows the collapse of the I-35W bridge. So after that, I believe the mandate require all the major bridge designed without fracture critical members. This is a Marcy Bridge. It's a pedestrian bridge. It's still, I believe it's a steel box girder bridge. You can see the girder is twisted during the construction. So that means this picture shows the inside the box girder detail. So you can, so it's very important to make sure the steel beam is collapsed. The steel beam is stable during the construction. So it means you have to provide enough diaphragms or internal or external diaphragms to make sure the steel girder won't buckle during the construction. Once the deck is hardened in place, typically the bridge should be safe. Here's another picture of twisted steel box girders. This picture shows the pre-stressed precast concrete beam bridge collapsed during the construction. So you can tell right away the end of the concrete beam is not braced. So if they brace the beam at the end of the girders, should be okay. Here's the Wacoda Bridge. Existing bridge is it's arch bridge. The new bridge is a two-cell segmental box girder bridge. It's a very wide bridge. There are only 3 webs. And the bridge, I think it's over 100 feet wide. During the construction, they found some like a cracking during the webs, which means, well, for segmented bridges, they are not supposed to be cracked because you design all the components with zero tension. So which means you have to check all the principal stresses for every component. And here's the finished product. So I think after they found the cracking in the webs, then they hired a person to perform the independent design. So then they proposed the internal post-tensioning to strengthen the bridge, even even before the bridge was open to traffic. I think the cost for this rehabilitation may be around $10 million. Now I'm going to talk about the Leo Frigo Memorial Bridge in Wisconsin. This bridge, I think in 2013, one or two piers settled by 1 or 2 feet because the corroded steel piles caused the piers settle. So you can see that after they remove the piles, they can see the severe corrosion in the steel piles due to the very corroded, very bad, I would say very bad the soil around the steel pile. So that means during the geotechnical testing, they should test the soil if they may cause the steel pile corrosion. So you have to remind the designers to thicken the steel edge pile to make sure they have, after maybe certain years of service, they are still okay after corrosion. Yeah, this bridge shows collapse due to the scour, due to the flood. So that's another big concern when the bridge is built over the river or creeks. Yeah, this is the bridge collapse during the removal of the existing bridge. So that means, especially for certain types of like a steel bridge built designed a long time ago, when they have those pin connections, so you make sure the removal sequence is correct. Otherwise, you may have this kind of problems during the removal or demolition. Now I'm going to talk about some repair methods. For steel bridge damage, typically use the straightening or strengthening on the damaged steel plate girders. Or you can replace the beams, which cost much more money, or you can strengthening the damaged steel girder with plating with bolted connections. For concrete deck, then you typically use the epoxy seal on the cracking, or use a partial or full deck repair. The last repair method, UHPC overlay, which is not common used. I think in Iowa they used the first UHPC overlay in US a couple years ago. Well, the problem is they last much longer than the conventional asphalt or other concrete overlay. The problem is the UHPC is a very expensive material. They cost about 5 times higher than the conventional concrete. So they told me the UHPC overlay could last for over 50 years, which is very close to the bridge design life. For typical overlay, maybe last for only 10 to 20 years. Here's this picture shows how to straightening the steel beams. This detail is from Illinois DOT. So you can see they use some like a timber blocking, then they Then they use some jacking to strengthening the girder to make sure when they bend it, they straightening back. Here's another picture shows the vertical strengthening detail from Illinois DOT. This detail shows the steel girder strengthening. So if there's damage, the girder may lose. The capacity is reduced, so you have to add a new place bolted to the existing girder to increase the girder capacity. Well, here just common superstructure repair for the PPC while pre-stressed precast concrete beam bridge. Typically use the epoxy seal on the cracking. You can use the fiber wrap to increase the flexible, the bending or the shear capacity. The last one, I don't know whether you could consider UHPC spray because I heard in Naperville, Illinois, they use the UHPC spray to strengthening the mantle. So I think maybe you can use to fix the problem as well. Well, here's just some common repair methods for the substructure. Use the epoxy seal on the cracking. Use the foam the concrete repairs or mortar repairs for shallow repairs. Then you could use the fiber wraps. I think for seismic repair, then you can look at some Caltrans, some standards. Here's some like a scour plan action suggested by Illinois DOT. So typically, I think mainly you have to inspect the bridge, like based on the frequency. So if there's an issue, maybe you should inspect the bridge less than 5 years. For typical underwater bridge inspection, it's once every 5 years. So in this case, you may have to inspect the bridge maybe every year or 2 or 3 years. And also you have to monitor the condition of the bridge. Identify the fixed scour monitoring device, which I don't know what kind of device you could use to monitor the scour or the potential bridge collapse due to the scour. So if you notice the bridge touching the superstructure or the approach roadway being overtopped, then you have a big concern for scouring. Well, here's my conclusion. So I think from these bridge failures, I think we first thing as a bridge designer, we need to improve our bridge design. Like for some major river bridge, I think we have to consider the vessel collision. I think personally, I think maybe from now we might need to consider the fire. Well, the bridge damage due to the fire, maybe we need to spray something to protect the steel girder from collapse, like a building steel members. I think they spray some material to prevent the fire, and also make sure especially for steel girder before they pour the deck, make sure the steel girder is stable for both the steel girders and the pre-stressed precast concrete beams. Sorry. Also, we need to consider some mitigations during the bridge design, and also we need more research on emergency repair on the bridges, how to make the bridge repair faster, or use some new material, use some like a new construction methods. Well, that's the end of my presentation. Any questions?
First question we have is, do they need to be preheated? I assume it was in regards to the last.
Yeah, for steel, you're right. For steel girders, if it's caused the damage I think some DOT allows preheating. I don't think Illinois DOT allow the preheating. I think I remember Pennsylvania when I was working on one steel bridge, girder bridge damaged by the truck. I think they preheat, then use some like a V shape, that kind of preheat pattern to strengthening the bridge, so to make the steel or bend it web or flange back to its original position. So I think it depends on the DOT, and also you have to look at the specs or special provisions to make sure they allow preheating, because I remember, I could be wrong, I mean, I remember Illinois DOT does not allow preheating.
Okay. Give me 1 second. We have more coming in. The next question we have is, can you please explain the reason to change the inspection period to 2 years?
I think that's a judgment call, because if you look at, well, I know in Illinois DOT they have like a structure menu regarding like more than a dozen bridge inspection, like a routine bridge inspection, fracture critical bridge inspection, or some like a scour underwater inspection. I think that 2-year bridge inspection just for the routine bridges. So if for some special inspection, like an emergency inspection, so when the bridge was hit or damaged by a truck or by something else, then they have to perform the emergency bridge inspection to make sure the bridge is still safe to open to traffic. Otherwise, they have to close down the bridge or posting the bridge, so make sure the bridge is safe for the people to drive on it.
Okay, the next question we have is, for ship collision loads are usually very high compared to vehicle collision loads. Do you think it's feasible to consider collision loads in bridge design? And is it very expensive?
Well, you're right. I think if you design the full collision loads from the boat, of course, it's very expensive. It's very expensive, and also you can design for it, just way too expensive. Typically, if you provide some dolphins, so that could mitigate the collision force. So they hit the dolphins first. So if the dolphin collapse, so then they hit the bridge pier, then the loads could be much less. I forgot, because I use this. I designed a pier for one of the major river pier to prevent the collision force long time ago. I think it's all depends on the river, the location of the bridge. I think if it's near the ocean, then the collision loads should be much higher than the collision loads for the bridge at Mississippi River, I guess.
All right. The next question we have is, for Slabtown Road Bridge over US 30 due to the impact load, it seems that there was no shear studs. Is that correct?
Yeah, I don't recall. I think they do have shear studs. Well, I think I forgot when they built this bridge. I think every bridge built after 60 or 70s should have shear studs, because that's how they invented composite girder design during that time. They should have shear studs. I think in the end, they just replaced the facial beam, because the facial is still good, just bend it too much. There's no way they can straightening the steel girder or strengthening the steel. So I think they just closed down the bridge, then they replaced the whole facial girder, then they replaced the partial of the concrete deck as well.
Okay, the next question we have is, AASHTO code doesn't seem to explicitly talk about how to consider preventative of bridges from fires. What code do you think we could use in this case?
I think that the building has a lot of experience regarding the fire protection. I think we might have to adopt some code, the fire codes from buildings, but I don't know. It's up to the DOT because the DOT is the owner, so they should make a decision. Right now, as far as I know, all the steel bridges are not designed for the fire. So that maybe that's something in the future the DOT should put something which could increase the vertical clearance, because when you spread that thing on at the bottom flange, that could increase the superstructure depth, then you can, which reduce the vertical clearance, so which means you have to raise the bridge by at least a 1 inch or half inch to accommodate the fire protection material. I think some research needs to be done for steel plate girders. I don't know whether, I think that the fire, because the steel girder is open, well, it's open to the air, not like a building. So building is pretty much enclosed, so building is much easier. The fire is much easier to damage the steel members than the steel girders to me. So I think they should do some research to test the steel girder, how to prevent the fire in the open air environment.
All right. Next question we have is, what are some commonly used scour repair methods being used in the industry right now?
Yeah, that's a very good question. To be honest with you, I think right now, all I know, typically they use the rip wrap, and the size of the rip wrap is based on the hydraulic study. So, but I heard some DOT do not consider that as a mitigation to prevent the scour. I think unless you inspect the bridge every year, so if you see some riprap wash away, then you put some new riprap back. I think as a designer, I think what we should do is after hydraulic study, I mean they tell you the scour depth. So when you design the piles or drill shaft, so it means that there's no soil around it. So I think you have to design for it, which means you have to make the pile drill shaft much deeper, much longer, because there's no soil around at the top portion of the pile drill shaft due to the scour washout.
All right. Next question we have is, how can you manage inspectability of the bridge structure versus coating with fireproofing? Would coatings inhibit inspectability?
Could you repeat the question again, please?
Sure. So the first part of the question asks, how can you how can you manage the inspectability of the bridge structure versus coating with fireproofing?
Well, that's a very good question. It's new to me. I haven't think about it. Maybe you can shoot me your email. Let me think about. We can discuss this issue. That's a very good question because, well, I think typically when they put off the fire, then they should be able to inspect the bridges. Well, the coating, that kind of thing, I don't know. Well, I think most time, if it's caused by fire, it's on the steel girders, then typically the girder will be severe damaged. I think most likely you have to replace that portion damaged the steel girders. It's very difficult to repair. The coating, I don't know. Well, for conventional painting, I don't think that they can prevent the fire, I mean damage. Yeah, shoot me an email. We can discuss a little more. That's a very good question. I think I need some more research to be done. I mean, well, at least the owner of DOT should put this topic in their research topics so they can hire some university to run the research for them.
Yeah. Okay. Well, Brian, if you'd like to discuss this further, we can definitely connect you with David. Moving on to the next question, we have for Pennsylvania box girder steel corrosion, almost all steel is corroded. What do you think is the main reason and how to prevent such corrosion in PPC bridge design in the future?
I think to me, there are a couple of things. I think the easiest thing is to increase the concrete cover. So that's the easy way to prevent the steel strength corrosion. The next thing is to use some non-corrosive material like a carbon fiber. I forgot the name. Like uses some not use steel strength. I think Michigan DOT has been using some like a carbon fiber, I forgot the full name, a strand to replace the steel strand, so which is not more, they won't be corroded. What the problem is with the cost, with the premium, I heard the cost is much higher than the steel strands, and also that carbon fiber strand was invented by Japanese. I don't know they still have a patent or not. If they do still have patent, which means the cost could be even higher unless the patent expires and everybody can make the carbon fiber strand.
All right, the next question we have is for the Tacoma collapse, was a consequence of the dynamic instability due to a phenomenon called structural flutter, when a variable superimposed horizontal load produced by wind gust effect increases the wind loads. Many texts erroneously describe the failure as an example of resonance, a completely different effect. To avoid this type of collapse, referring to the flutter, what would you recommend?
Well, typically right now for all the major bridges or long span bridges, such as suspension, cable stay, or arch bridges, you have to run the wind tunnel testing to make sure, I mean, the bridge is stable under different wind loads. Certain wind loads, make sure they are stable. Typically, you can improve the bridge stability by using deeper girders, heavier girders, or you can use some dampers to reduce the vibration.
All right. I think that concludes our questions. I don't see any more new questions for now. If at any point anybody does have any additional questions or would like to get in contact with David, you can either contact him directly or you can let us know and we will put you in contact with him. But this concludes our session for today. David, thank you so much for this amazing session. I know our audience really, really enjoyed it.
Okay, thank you very much. Bye-bye.